Afternoon, one and all. Am I audible?
Yes.
Okay. Thank you. Thank you for the feedback. So, good afternoon, all. Welcome to the second day of this ATAL FDP on advances in artificial intelligence. So, like yesterday, today we will also have three sessions, and the guest for the first session is here with us. He is Professor Kandarpa Kumar Sharma. I take this opportunity to introduce Professor Sharma. Dr. K.K. Sharma currently serves as a professor and head in the Department of Electronics and Communication Engineering of Guwahati University. He specializes in deep learning, wireless communication, speech processing, and antenna design. He has obtained PhD in the area of mobile communication in 2012 and MTech in 2005 from IIT Guwahati. He is also a senior member of IEEE. So today, Dr. Sharma will be discussing about predictive computational aids for monitoring seismic activity, state-of-art technology, and trends. So welcome, sir, once again, and it's a privilege to witness you in our session. And thank you very much. And over to you, sir.
Yes. Thank you. Thank you for your nice words. I will be now sharing my slides. So let me come to the second slide. The second slide is coming.
Yes, sir. Second slide is coming.
Let me go back one more time. The first slide is coming.
No, sir.
No. Okay. I shall stop sharing and then share it.
Yes, sir. Sir, try to share the whole screen instead of a single window. That usually works for PowerPoint. Try to share the desktop, sir.
Desktop, okay.
Yes, sir.
Share, okay. Now?
Yes, sir.
Now,
sir, you can make it in the yes, sir.
Now,
it's coming, sir.
Now, second slide is coming.
Yes, sir.
Third one.
Yes, sir.
Okay, great. Okay, let me go back to the first slide. Yes, let me start. Good afternoon to you all. I am starting my slides. I'm starting the presentation. So my presentation is titled Predictive Computational Tools for Seismic Monitoring, State-of-Art Technology and the Trends. So this is the plan of presentation. I will be speaking about the background, why we need a monitoring system for the seismicity, what are the prediction practices currently being used, the predictive tools and the computational tools, where we can use the predictive computational tools for the monitoring of the seismicity and the seismic activities, a few case studies, and then we will conclude. Now, why we need to monitor the seismic activities? We all know that the seismicity leading to the tremors and the earthquake worldwide is a major reason for the loss of life and property. And the current technologies are not precise sufficiently. So hence, globally there is a challenge, and work is going on in a concerted manner to make the forecast of seismic activities to be more reliable. So therefore, worldwide there is a coordinated framework for the study of seismology. At the top is one platform called the IUGG. That is then there is one more such platform called the IASPEI. This is the International Association for Seismology and the Physics of Earth. Then there is a Federation for Digital Seismograph Network. Then there are a range of satellites for in the LEO capability for the monitoring and observation of the Earth. Then there is a European Seismological Commission. Then there are Euromed frameworks with laboratory research facilities, and there is a specialized Mediterranean Seismological Center. All these frameworks have their own board of directors and governance, participants, and governing councils. Then let's see some challenges regarding the earthquake seismicity. So earthquake monitoring has been taking place for roughly about last 200 years. 1895 to be the precise, where the first standardized version was brought into the practice. Now, the study of the seismological data started since 1950s. Use of signal processing, tomography, noise cancellation, noise imaging, then computing technology. These are coming in a big way. And there are data challenges in the observational sites, primarily related to the gathering, monitoring, transfer, storage, then leading to the real-time information processing, quality linked with the metadata, quality control, formatting standards, and how we store it and distribute. Then there are data challenges on the modeling side. These are related to the wave propagation through the complex media, rupture process modeling in the inhomogeneous media. Then more recent data challenges linked to the earthquake seismology are linked with the matching modeling and the observation, waveform inversion technologies, which are linked with large amounts of data and computational resources, rapid near real-time data dealing or processing for rapid earthquake monitoring and warning, ranging from seconds to a few minutes. Then tsunami warning, rapid seismicity content capture, then broad data access and availability for scientific research, then distributed resources like combining data volumes, computational resources, shared data tools. Then here is a global seismographic network, quite big, and these network details are there in the Google. So the network shows that its distribution is quite worldwide, very much all spread all around the world, and we can see that most of these are spread around that Pacific and the European. So we find that the seismographic networks significance are felt in these particular regions because these regions have high seismicity record, or they show seismographic behavior. Then there are a few more recent developments where the works being done by the US government through their global seismographic network and the National Earthquake Information Center is doing very significant work by collecting the seismographic activity of all the world's major developments. So here are some of the lesser known but very significant seismographic networks. One is the Milne seismographic network. Then there is a network called the Zesut network. It is working from 1930s. Then there is a worldwide standardized seismographic network. Then there is a network by the name. Then there is a network by the term IRIS USGS Global Seismographic Network, and then there is one more network called the Federation of Digital Seismographic Networks. Now these particular networks mostly record the seismicity that are captured by sensors, and mostly in form of tremors, the earthquakes that have come all throughout the last two centuries, from 1900 until up to the present time. And how they record, here is a depiction. Now the Earth, since is quite dynamic below, its core or its center is quite volatile. Therefore, people use tomographic and waveform forward modeling for doing the study of the Earth's core, and that way try to develop some know-how regarding its seismic behavior. So there is a European network by the term seismic wave propagation and imaging in complex media. This particular framework continuously keeps an eye on the Earth's seismic behavior by studying its core through the use of the waveform tomography principles. Then earthquake rupture modeling linked with the strong motion modeling is a standard practice preferred by geologists for studying the seismic behavior in specific rupture regions, or regions where there are chances of rupture, which can lead to big tremors or big seismic behavior, or say even tsunami. Now, seismic imaging, here there are a few cases. We can see that the tomography can capture group velocity. These can also map a special type of wave called the relay wave, which is responsible for a lot of destruction. So these type of maps or techniques are vital for monitoring the seismic behavior that we see all throughout the Earth's surface. Now these tools are very much necessary because there are significant chances of damage, loss to life and property. Therefore, the real-time and rapid warning related to seismic behavior is quite necessary. Since all the physical structures that we have all throughout the Earth are quite vulnerable for this seismic behavior. So therefore, the seismic behavior is linked with certain forecasting. Short-term forecasting may be there. It will be mainly confined to days. Then long-term forecasting can be linked with years. Then long-term damage mapping can be spread around as decades. So such forecasts can lead to short-term warning, medium-term warning, and long-term warning. So these type of warnings are quite significant and are closely linked with the seismic monitoring and prediction. Now here there is a portal called the seismicseaportal.eu that shows the waveform generated, regions data generated, the magnitude, latitude, longitude, and all the related details in a web form, in a web portal with the related data. Now this is a free website where there is a continuous recording of all seismic behavior captured by sensors linked with this seismicportal.eu. So this particular portal, this particular web service has turned out to be a secured and reliable source of data for the design of computational models for dealing with seismic monitoring and model development. Now, how the data are captured? Here is one such depiction. So there can be year-wise or date-wise or month-wise variation. So these there in the first plot we see that there are large-scale Richter scale records depicted. Smaller scales are not depicted, but in the much smaller scale, year-wise, say variations starting from 0 and then say beyond, those can be also recorded on the surface level and below the surface level, sea level also. So this type of continuous recording, this type of continuous seismic or Richter scale recordings are captured by the networks and shared worldwide. So here is a record captured by the sensor, by the seismicity sensors related to the Kamchatka Peninsula in the Pacific, close to Japan, where the seismic behavior is quite high. So how the drift of a particular region, how the region is seismic region, how it moves, the cumulative movement, how it is recorded by the sensors per year, per decade. This is shown. So this type of data were also recorded by the sensors. So it shows clearly that there is a huge volume of data generated. So the data volume generated till up to the 2020 limit. The global trend is more than 100 terabytes of data per year. This is coming from, say, the high quality measurements. Then if we go for the mobile setups, acceleration setups, where there are mobile facilities to check the seismic behavior, these will be generating data volumes between 100 to 500 terabytes per year, and then a miscellaneous set of sensors together generate further 200 terabytes of data. So we find that seismicity or seismic monitoring is a big data scenario. So it generates continuously high volume of data for which proper computational tools and models are required to perform simulations, to perform or to develop model or to develop prediction technique. So proper computational tools are required. So for that, specialist computation frameworks are developed and are in practice. One is called BioWolf in Caltech, Then there are supercomputers in Jamstack, Japan. So these are there which deal with the data and computational model development, especially from the data captured from the seismic networks. So how are the frameworks working together? So here we see that seismic behavior in a global framework come through permanent networks. Some of these come from satellite frameworks or satellite facilities. Then these come from say that the in situ sensor networks, experimental laboratories, and then related laboratories. Then further records come from the temporary deployments, sensors linked with the study of the volcanoes, data mining packages, and computational facilities. Then there are significant networks that are dealing with the seismic behavior that are linked with the sea surface. So all these together are coming continuously. They are generating huge volumes of data per year. Now, in the local level, how a seismic data recording takes place, this slide shows. So there can be a group of sensors. The sensors are deployed there in the surface. Sensors can be placed in the or can be dug there in the surface of the earth. These can vary from 10 meters, 50 meters, 500 meters, 1,000 meters, 5,000 meters, like that. So at different depth, these sensors are deployed. So there shall be digging of the surface of the earth. These sensors will go down below the surface of the earth, and they will be placed there. And these will continuously record the seismic behavior that are taking place at different depths of the surface of the earth. And then there will be a central recorder recording all those sensor readings continuously.
Sir, I have a question. Sorry to interrupt you in between.
Yes, please.
Sir, when we are placing these sensors, how are these placed and how that information is recorded?
Okay, so these are mainly done by the geologists. Geologists study a particular region. So as like we do the drilling for petroleum, there are special drillers, drilling tools that will drill and place all these sensors through long pipes. So long pipes are sent down through the surface of the earth, and those seismographs are placed at different depths. And then
so this information might be confidential, like whatever they are recording or studying. So is it freely available over that website?
Yes, freely available. These are freely available. All those sites that I showed, these are there.
Okay, sir.
So these people can use for doing their study, research, development of the computational tools. These are very good data, and these seismic data normally are shared. There is no such secret thing. If it is not linked to a very sensitive place, I know that the Kamchatka Peninsula in Russia, close to Japan, that is quite a sensitive place. So there might be some sort of secrecy, but normally in most of the cases there is no such secret thing, and these are normally shared.
Okay, sir. Thank you, sir.
Then we find that there shall be all these recording take place in the real time. So several such seismic recorders. So here there is a central recorder. So it will be a centralized recorder, and all the sensors normally nowadays will have fiber or coaxial cable connection. So with these connections, a physical communication network, several such seismic recorders form one local network, and they are then connected to a computer system that will be collecting the data continuously through software designed for such purpose. Then finally, while the data is recorded from different field stations, these are passed through several signal conditioning processes. And while the signal conditioning processes are carried out, GPS locations are planted in the field station data, and that way they are passed through to a digital recording system, where if there are specific or notable variation in the Richter scale, then a triggering will take place. That particular triggering will send messages to mails, to phones, and all that to governments, telling that a 5 Richter scale tremor took place there. So this way the whole thing is done. So all these field stations. So one such setup shall form a field station. So several such field stations will be linking up, and then will send the data through a processing software with GPS details collected and planted, so that it gives us a real-time seismic data continuously. So this sort of signal conditioning is required for continuous recording of the data collected from the field stations. Then the real-time seismic collection center, based on all digital framework, can have GPS provisions with the field stations coming in with the data feed, and these might be connected through fiber networks or wireless networks. So this will come to a zonal level facility, where there will be processing software and digital recording for storage of the data, for database management, and then further dissemination. Now let's come to the long-term forecast methods, or the forecasting methods. First, we will focus on the long-term methods. Now, long-term methods, these were there for quite some time, for the last several decades. These are primarily linked with a study called paleoseismicity. This particular field is called paleoseismicity. So here, geologists will go and try to find out fault traces, where there are trends, where there are sedimentary layers are formed, and then find out if there are material behavior changing. So this is a very ground-based work. A groundwork sort of field work is there, where geologists will go to field and study. This is linked with the long-term seismicity study. Now, this particular seismicity study, we can find out primarily being carried out in the river beds. You might be quite familiar with big rivers. In our state, we have the river Brahmaputra. So when Brahmaputra dries up, you know that Brahmaputra flows from Tibet, and when it comes in and dries up in the winter time, then geologists might go and find out if there are new faults developing in the river bed. Similarly, this type of seismicity study can be done when somebody goes to a hill, a mountain. So those hills, mountains, or similar type of geographic locations can give this type of variations linked with the fault trace, trends, sedimentary layer variation, and like that. So this type of seismicity patterns have led to the prediction of more than 70% of the big tremors with scales of greater than 6.7 in the last century. They with this sort of behavior, they have prepared a list of big tremors that might take place between 2000 to 2030, and it has a precision of or reliability of roughly around 70%. So this is a method of doing the forecast. Then there is a philosophy that the geologists follow while doing the prediction linked with the recurrence. In the northeastern part of our country, we saw that this sort of a recurrence took place. So with big scales. One was in the year 1896. There was a big tremor, a devastating earthquake took place, and it was one more time repeated in 1950. It was further big. So there is a statistical periodicity with such big tremors, people say. So this is one more method for doing long-term forecast. Then fault variation is one more method of doing long-term prediction. Fault variation means there might be large-scale surface variations in the seismic gaps. So this leads to a stress development or strain development below the surface of the earth, for which there might be ruptures lead to release of huge power, and that leads to destruction. So the variation of the faults, movements of the surface in bigger volumes is one more method for doing the forecast. So with this sort of study, the pattern of seismicity monitoring by focusing on fault variation have been used for doing the prediction of many such big tremors. One such case is in Turkey that took place in 1937, and several such cases were reported subsequently, and these are linked mainly to bigger scale tremors of 7.1, 7.0, 7.3, like that. Now let's come to the probability of earthquakes that has a magnitude of 7 or greater in the next 30 years. So here we can see many studies are being done. Mainly these type of big seismic behavior are being thought to be concentrated in the bay regions. So the sea is one such source where such great seismic developments will be taking place. People believe like that. Now let's come to the short-term prediction. These are based on the precursors. So short-term prediction provides a reasonable time period. Method is based on location fault or fault segment detection, and further focus on the magnitude. So here these are mainly focused. The sensors will be trying to find out if there are deformations taking place. So deformations, we can see that this is a depiction of a surface of the earth before the earthquake took place. This is during. So this is a relaxed space. This is a stress space, and this is a release. When the stress is released, rupture takes place. Then the destruction will take place. So the ground deformations are one such methods through which we can make short-term predictions of the earthquakes. Then there is a special gas called the radon gas. This will start to come up or come out if there is a probability of high seismicity. So if a tremor will take place, radon gas will come out. Then people believe that all the zoological species, maybe dogs, the tiger, animals, they can also sense variations in the electrical and the magnetic fields. That way they start to show very strange behavior. So these are also used as rapid or short-term prediction methods. Now let's come to the computational models for seismicity monitoring. So one of them or some of them are based on grid computing. Some of them are based on cloud computing. Some of them are based on learning-based techniques. Lately, the learning-based techniques are coming up in a big way. So the grid computing-based techniques combine here subsurface sensors, sea-based sensors, the surface-based sensors, and the satellite-based sensors. So the earth-based sensors, the subsurface-based sensors, the satellite-based sensors all use different spectrum ranging from the ULF lower frequencies to the very high frequencies to continuously monitor the earth and the surrounding for seismicity, for seismic variations. Then seismic monitoring nowadays takes place in a computational cloud. All throughout the world, governments have deployed computational clouds which continuously record not only the seismic data, but they start to develop, or they can give predictive trends or the prediction of the likely seismic behavior in the subsequent future. So that way, computational cloud specifically related to the seismic monitoring has developed during the last few decades. Then we come to the predictive and the soft computing models that have come across for use in the seismicity or seismic behavior model design. One of them, or a large part of them, are based on the fuzzy principles. Fuzzy principles being based on the work of Lutfi Jadeh, who is the father of fuzzy logic, define such computational soft computing techniques which are found to be very much required for development of real world like processing. So these soft computing techniques are based on perception. These are flexible, robust, low-cost solution and has close resemblance with human-like decision making. Therefore, are quite beneficial for the use with seismic behavior monitoring, and that we use them for predictive model design. So we know that there are a few components of such soft computing models. A few of them are based on neurocomputation or the artificial neural networks, deep neural networks, and fuzzy systems. Now, for all these tools, there are two phases. One phase will be the learning, and the next phase is the testing. So one of them can have a reference pattern in the learning time, and once the learning part is complete, these can be deployed in the field for doing the continuous monitoring and prediction response generation. Now, how can we use the learning-based tools for the monitoring of seismic activities? Now, in most cases, we find that the sensors generate a seismic electrical signals. So these will be generated at the epicenter, and these will have magnitude variation when there is a probability of a tremor taking place. So these will vary from a few seconds, days, or say minutes, and these will be recorded as transient variations. So it can be from a few tens of volts to picovolts per meter, depending upon the strength. So these can be captured by a network of seismic sensors, then can record them as waveforms and then feed these to a learning-based tool. So now there are two types of seismic waves. One is called the body wave, and the second one is called the surface wave. Body wave travel normally through the Earth's surface, that is below, and the surface waves will be limited to the Earth's surface. Mainly similar. These are similar to the waves that we see on the surface of the river, surface of the sea. Now from the body wave, we have one wave of the primary wave, that is a operational wave. So this is the first kind of body wave which travels fastest. So it can have a velocity of 6 kilometers per second, and it travels through the crust. So it can move through solid rock and say fluids, water, and so on and so forth, and it will normally generate compression while it goes. So this primary wave will be a first sign of a tremor taking place. Then there is a secondary wave. So this secondary wave or shear wave, it has a speed of about 3.6 kilometers per second while it goes to the crust, and it moves rock up or down or sidewise, side to side. So it is a secondary wave, a much lower wave. So the primary wave is quite fast. Most of the destruction will take place from the primary wave. Secondary wave will be a follow-up wave that will also lead to destruction, but this wave is somewhat slower. Then there is one more wave called a love wave. This term love wave comes from a British mathematician by the name of E.A.H. Love, who worked on this particular wave and created a model for it. This is the fastest surface wave and moves through the ground side to side, and it shakes the buildings. Then there is one more wave called the relay wave. This is a kind of a surface wave, and the wave's name comes from Lord Rayleigh. Now the relay wave will roll all around the ground like a wave that rolls around the surface of the water. As it rolls, it moves the ground up down, and that way it moves side by side also the same direction in which the wave is going, and it generates lot of shaking. So during a tremor, the shaking that we feel is due to the combination of the relay wave and the love wave. So L wave and this R wave, these two are the waves that will be generating the shaking that we feel during the tremor. Then all these data that are coming in different waveforms. They can be processed, or their waveform characteristics captured, and their properties recorded with spectral, statistical, and time varying properties. So from these waves, we can generate the relevant features, which can give us a set of patterns that can be fed to the learning system for making the learning system to learn, and that way develop the predictional tools or the predictional models through which a forecast regarding a tremor can be given in short term. So how the pre-processing data and classification can be done or is done normally? Here is one such depiction. So we can find here that there are different components. So one of them is a magnitude vector. It shows some of the negative cases and some of the positive cases. Then once the tremor goes, there will be aftershocks, how they will look like. So these are labeled this way. So this forms a pre-processed level data that can be used for feeding a learning system. Now, similarly, we can here find a set of sensor data which are calibrated, which are labeled for making decisions by the use of a classification system. So if we use this sort of a data, the predictive model that we require can be roughly summarized to be something like this. So we have the sensor data. From there, we'll be doing the pre-processing or the feature extraction. This can be based to a classifier, which can be a learning-based tool. To that learning-based tool, we may feed a decision logic beforehand, and then generate a prediction or monitoring decision. So this is quite similar to a pattern recognition system, where there will be a sensor, a pre-processing mechanism, a feature extraction process, a classification mechanism, and a decision-making system, which is based on model design, cross validation, and decision generation. So so let's come from the very beginning. So since we know now that there is a prediction part, so one very basic method of generation of the prediction capability comes from the perceptual learning rule that was first proposed by Rosenfeld in 1958, where we know that a decision plane can be moved by continuously varying the weights of present there in a connectionist link of a perceptron. Now this particular method of changing the threshold leads to a learning taking place, but it takes place in a very limited scale and is useful for less complex problems. But when we combine several of these perceptrons or neurons linked with the perceptron learning rule, these form the ANN or the artificial neural network, which is a popular prediction tool used all throughout the last few decades. This can be used for learning patterns and that way develop prediction. So it is a biologically driven computational tool which is of non-parametric type. It means that it is not much concerned regarding the source of the data. It just needs data and some levels through which it can learn the patterns and that way generate some decision. So we know that such neuro computing structures or the ANNs are quite reliable structures formed by simple neuron-like threshold switching blocks. They have many weighted interconnections, highly parallel and distributed processing supporting, and learning by tuning the connection weights. So one such network where this sort of complex pattern learning takes place is the multi-layer perceptron, where there are multiple middle layers through which the learning takes place. Learning will be held and will be used subsequently when we the patterns. So based on propagation has two steps. One is a forward step and one is a backward step. And between these two steps, the present result and the desired result
अभी मजाक में मैंने बोला तो आता मीटिंग मध्ये म्हणणार रात्री 10:30 वाजता येईन म्हणले आता वाटत होतं की हा म्हणतो आवते असं
Yes, sir, you can continue, sir. Professor Sarma? Hello. Professor Sarma, your mic is probably muted off. Yes, sir.
Okay.
Thank you, sir.
Thank you. So, so we find that one more such prediction tool is based on the fuzzy systems. These are developed based on the fuzzy set theory proposed by Lutfi Jadeh. Fuzzy sets are different from the crisp set due to the use of the statistical membership functions, which develop several stages between the limits set by the crisp set, high and low, 0 and 1. So that way, subtle variations between the states high and low can be recorded. This sort of subtle variation recording is quite beneficial for making pattern recognition systems reliable. So hence are quite popular with the use of prediction tools. So if we design a fuzzy-based prediction tool, we should remember this is based on the perceptions defined by the use of predicate logic and the probability theory. Therefore, if we have a crisp set coming from the real world, these will be passed through a fuzzifier, will go to a decision-making device that will have support from a fuzzy rule base. It will generate a decision. This set of decision is defuzzified and a crisp response is generated that will go to the real world. So some of the cases that you see are very well defined by the use of the fuzzy sets are like very, very young, not so old, direction, slightly left, sharp right. Then fuzzy set can deal with perceptions like desirable city to live in. So therefore, that way fuzzy systems have become very closely linked with the machine learning. So the core concept for grouping various technologies with the capability to learn and recognize patterns, since forms the base of the machine learning, can be also grouped with the fuzzy system. That way, in the fuzzified form, we can have a measurement space. From there, we can generate the features to form the feature space, which when goes to a decision-making device can lead to the generation of decisions that form the decision space. Then further, there is one more learning-based tool which is used mainly for the optimization purpose. This is called the genetic algorithm, or GA, that is based on the Darwinian principle of survival of the fittest, which works primarily to generate the best solution by the use of a fitness function. So there are several steps. First, a set of solutions are proposed from the parent and the child, and from the parent processes. Several child processes are generated due to the use of the mutation and the crossovers. So then the child processes generated by the use of the crossovers and the mutations are fed to the fitness function. The fitness function that has the maximum value for a particular child process turns out to be the most likely solution. So this way, the optimal solution can be generated from a lot of solution sets. So GAs are found to be that way quite reliable and are used for resource conservation as part of learning systems. So how from the parent processes, child processes are generated. The line can be a crossover plane used for mutation and crossovers. Therefore, all these tools together form the machine learning domain, which is geared primarily to develop the capability to generate human-like decision making. So these are commonly considered as part of the AI. So the AI represents a set of methodologies which permit the machines to decide and work like human beings. So therefore, AI has a subset of machine learning has a subset of deep learning, which when is combined with big data situation constitutes data science. And therefore, we can say that seismic monitoring is a big domain of the use of deep learning. That way is a fertile ground for data science. So machine learning we have gone through, we'll skip this slide. And where we use machine learning, we use machine learning when there is a blind situation. We do not have sufficient know-how. So if we want to navigate in a very distant place, we are not sure regarding the route and the navigation details, we can use the machine learning tools. We can use machine learning for doing speech recognition, personalized or customized solutions for medicines. We can then deal with genomics or big data situations by the use of the learning-based tools. So we can say that that where there is big data, where there is lot of huge volume of data, machine learning grows and survives. So this is a very classic case of the use of the AI tools through which we can get rid of the repetitive task that a postman faces in a post office while while distributing the day, and the letters, and while reading the mailing address and classifying the destination of the surface mail. So if we want to get rid of repetition of tasks, we can use a machine learning tool for that. Many of the tasks solved by the learning-based systems cover face recognition, then recognition of or suspicious transaction, can deal with suspicious sensor readings in a nuclear plant, can deal with predictions of the stock market. So the difference between the traditional programming and the machine learning programming can be shown like this. Then in the traditional way, we find that in a computer system, we need to feed data and program together to generate a response. But in the case of a machine learning system, we have a computer. We can give the data and what we want as a response from the system. The computer at the state when generates the desired response, that particular program, we call it to be the machine learning program that we want to deploy for practical situation. So therefore, we can summarize that learning systems capture the patterns fed to it, retains the captured data and use it subsequently, have the capacity to take decisions, and can also replicate biological learning. But learning systems require a model, a domain, and source of data. So model, we can say that model is a computation logic, a mathematical set of functions which in a logical way or in a computer program form is deployed on a computer system that will run on a CPU with memory and devices connected to it. And this particular model will develop the learning required for a particular domain by the use of data from a particular source. So there are 4 types of learning that we come across: supervised learning, where there is a level or where there is a reference. So the training data will have levels of the desired response. Then there is the unsupervised learning, where there is no prior level. So training data does not have reference. It deals with a blind situation. Then semi-supervised learning. Here there is a type of learning where there will be some sort of supervision and some type of unsupervised method of doing the learning. And then there is a reinforcement type of learning, which is based on a reward or a voting methodology of developing learning in the local level. So here is a form of supervised learning. So we give the patterns and the target together as pairs. So we want that both the red and the green lines to coincide while dealing with the data. So there are data levels or data with levels fixed before him. So supervised learning can tell us what to do, what to classify it precisely. But again, we need level data or previous references. But in the case of unsupervised learning, we give patterns. So the patterns will come here without levels. So here some sort of a clustering will take place. This sort of clustering will take place by following some sort of similarity or by discovering some sort of similarity between the patterns. The statistical mean of samples with certain similarity will become the cluster structure, and the cluster around that cluster center will be created. So if the data in the left side comes with various colors, data in the right side will start to group in specific colors, green, blue, and red, but they will start to group around a cluster center, which will be a statistical mean of that particular set of samples. So unsupervised learning is quite frequently used for separating out speakers from a clip of voice where two speakers are speaking together in the crowd. This way, that means speaker 1 and speaker 2 will have commonality, or will generate data with commonality. The clustering or the unsupervised mechanism will discover the commonality in the combined clip and separate out speaker 1 and speaker 2 by the use of some sort of clustering. So therefore, we can find that machine learning and deep learning roughly are governed by three types of learning: supervised learning, unsupervised learning, reinforcement learning. With the use of supervised learning, we primarily carry out classification and regression. Classification is to place groups in specific classes. Regression is to replicate a classification decision by the use of situation A and replicating it in situation B. So similarly, in the case of unsupervised learning, we can use it for clustering primarily, and reinforcement learning. It is based on rewards, and it is mainly a localized decision-making process based on maximization of voting. So the state of art now of the machine learning is best demonstrated by the autonomous car technology, which tries to replicate the behavior that we see while driving a car by a person. The technology deployed there will be keenly following the driver, and the technology will be capturing the road that the car takes while being driven by a person. So there will be sensors like camera, laser terrain mapping, proximity sensor, and route navigation. So the combination of laser terrain mapping, proximity sensor, route navigation will generate a sensor fusion by the use of the machine learning tool, and the tool will closely try to replicate the driving characteristics of the human driver. The vision coming to the car from the camera will change as per the lighting conditions. For night time also, there will be capability of navigation, daytime capability of the camera shall be used for developing proper navigation details. So we find that the driverless technology, or the autonomous car technology, has reached quite a mature state, which reflects the true state of the state of art of machine learning. So the trend nowadays is to move towards deep learning, which turns out to be a specialized form of machine learning that supports learning by its own. So the machine no longer is dependent on the human programmer. So we can find that deep learning has turned out to be a subset of the machine learning based on more complex neural network structures and is more data driven. So we can see a striking difference between the machine learning and deep learning from this particular slide. So we can see that as we shift towards deep learning, the human role is slowly decreasing. Machine dependence is rising. So so the data's role is coming out to be more prominent, and here there is a marked change towards the use of detailed content learning or detailed content processing. Previously, the role of the human programmer was to develop a feature set best suitable for doing the classification. In deep learning, the feature set is no longer required. So therefore, if there is huge volumes of data, from the data, the network can do a detailed feature learning and generate its own features and use that particular feature to perform or carry out classification. So that way the complexity of the networks have changed radically, and the method of feature learning too also has changed quite dramatically. So we see that the previous generation neural network looks like this. In the left side, there will be one or two middle layers that will have considerable amount of connectionist links, but the present day deep learning neural network will have a thick middle layer. Many more layers will come. In the previous case, what the human programmer fed as features, the neural network took, and it will try to replicate the patterns that are fed to the network as target. So the target shall be there. Targets will be replicated. The network will try to follow targets, but it no longer. But in case of the deep learning neural network, the target specification is not a very mandatory requirement, though in the supervised cases targets may be specified. But its learning methodology, why it is deep? Because we find that there will be learning layer by layer. So from the left side to the right side, more complex features shall be learned. So while we move from left to right, the feature learning will be more detailed, will be more content rich, more relevant features will be captured. That way, the reliability of the network will grow. So if we are dealing with a face recognition task, we find that the leftmost layers will learn very delicate or less detailed features. As we move from the left to the right, the depth of the learning will rise. More detailed features will be captured. Subsequently, while it comes to the rightmost layer, more detailed relevant features will be generated, which will go on to the classification layer. So that way, layer by layer, learning will take place in the deep learning structure, which will raise the level of reliability. So we can say that deep learning's basic consideration came from the traditional neural network structure. It came because researchers were trying to find out if the traditional ANN had deep learning characteristics. So while doing so and while suffering from the local minima problems with the backpropagation learning, deep networks develop, which have characteristics like it has more number of middle layers. It uses feature learning. It no longer requires, or it may not require, data labeling, but it requires huge sets of data for doing the training. So why deep networks develop? Deep networks develop because previous generation neural structures suffered from the local minima problem linked with the backpropagation technique. Feature learning was never satisfactory, required prior learning. Concurrent and continuous learning rarely took place. Difficulties while dealing with rising dimensions of data, and the world started to recognize the limitations of the previous generation neural processing, and therefore felt that there is a need to shift to the next generation. So this was reflected by the continuous rise of research publications between 2006 and 2016. There was more than 3 times rise in this decade. Then further, one more reason why deep learning developed so fast, because there was simultaneous growth in the big data scenario. Seismicity study or the data link with the seismology is one such field. Further, there we saw a tremendous growth in the social media domain. So while the world dealt with 16.3 zettabytes of data, by about 2021, this rose to about 58.45 zettabytes of data, and by 2025, 162 zettabytes of data limit shall be crossed. So this big data scenario, due to the digitization in all sectors of human life, has seen a tremendous growth in deep learning too. So lately, people find that that deep learning is driven by a wish to convert data to knowledge and subsequently to wisdom, because people feel that it has benefits for the humanity. It has given growth to cyber physical social structures where all types of networking are taking place, where the study of seismicity too is also very closely linked, because it is linked with the human life, human safety. So therefore, big data scenario combined with the learning tools, formulating data science is primarily focusing on map reduce, frequent search sets, similarity matching, clustering, dimension reduction, streaming of data while dealing with big volumes of data. And for all these things, learning-based tools have become very significant parts. There are a few topologies that are quite commonly used in the deep neural network. A feed-forward network with many layers, many middle layers, can be a deep neural network. So it can support layer by layer feature learning, and that way have significant feature capturing capability. Recurrent neural networks are used where there are sequences, where there are time dependence. So the previous case was a feed forward network. Recurrent networks are networks where there will be feed forward and feedback networks. So with the feedback networks, we can deal with time varying data. So time tracking, contextual processing, these things come into the picture. So for the study of seismicity, for seismicity measurement, for seismicity monitoring, the recurrent networks are very relevant. For pattern generation, deep neural network in feed-forward structure with multiple layers can be also used. For more detailed feature learning, for feature learning driven decision making, convolutional neural networks are used, because convolutional neural network, by the use of the convolutional process, reinforces the feature learning process. And since the convolution in 2D and 3D form, by the use of filter masks of varying size, 2 by 2 or 3 by 3 or 4 by 4, permits a very detailed capture of the samples fed to it. That can be one dimensional data, two-dimensional data, tensor of data. So data dimension is no longer a factor. Therefore, is quite relevant for big data situation. So it helps to deal with very complex structure of data, complex size of data, complex dimensions of data. Therefore, is a very relevant network for the study of seismicity. So these type of networks are used for generating a short-term forewarning. These sort of networks can develop the P wave and can tell also the capture of the secondary wave. Therefore, can generate short-term forecast. These were used successfully in Japan for detecting a tremor, and it gave notification 10 minutes prior. The Kobe fault, as part of this pre-warning, was found to be the source of this seismic behavior. It further gave to the rise of tsunami. That particular forewarning also came through this particular system. Then CC wave, that Taiwan 1999, it was also detected by the use of neural structures. That was a few cases reported in the late 1990s. Nowadays, many such network structures are in deployment. The US forewarning system is there. It is quite costly, being built over a 5-year time. It can detect the P waves and give warning 3-4 minutes prior, which can help in generating the precautionary measures. So there are several case studies. I will come to a few latest. Here is one of them reported last year, 2021. So here they have used spatial temporal data by the use of and fed it to deep learning networks, and generated a reliability of 78%, 78 to 79%. So quite a significant work. Then they have used a structure of this type. They have used data from those seismicity websites, and then placed it in different types of, mainly based on CNN structures. They have fed data zone by zone. That way developed the magnitude variation classification. They have done a four cross classification and focused on the reliability and the sensitivity. They have used a combination of classifiers, shallow network support vector machines, and then deep neural networks. Then there is one more reported work last year that is based on the Google Kaggle platform. Here it is based on a US lost Alamos laboratory, very famous, and a group from the Purdue University. So they have shown how how real-time sensors can be used for capturing the shear stress and strain, and then used it with the Google Kaggle platform for generating prediction. Then one very famous work reported last year in the Nature Communication is linked with the transformer, a deep neural structure transformer that can simultaneously do a earthquake detection and phase picking. They have used a very complex network which supports end-to-end deep learning, It is a combination of recurrent and convolutional neural networks. It has several coders which are mainly capturing the features and separate decoders for doing the detection. So the network structure looks something like this. So let's come to the conclusion. We can say that learning-based predictive computational tools are reliable means of monitoring and predicting the seismicity, but within a tolerance window. Success depends on a network of sensors, pre-processing, application of prior knowledge, and properly training the learning-based predictive and computation tools. So before I conclude, I would like to request the participants to raise a few questions.
Thank you, sir, for your talk. The participants are requested to ask any questions if they have any doubts to sir. Dear participants, if you have any queries, please ask.
Yes, I will share my slides, and if they have any doubt, they can also mail me. So I think I have tried my best. I don't know if the participants are benefited or not, but I tried to bring in a new dimension in the use of the learning-based tools for developing predictive and computational tools for dealing with seismicity. Because our country is facing this, and this is a big threat in our northeastern region. We are a zone 5. We are in zone 5. So one
Yes,
big this thing will come. So let's hope we are on safe.
Yes, sir. And recently also, because the tsunami and the earthquake in Tonga, it has, people say that they have heard the sound after like 5,000 miles away also.
Yes.
And the tsunami waves have traveled to Peru, USA, New Zealand, Australia, everywhere it has. So your topic is very relevant now also.
Yes. Nowadays, people do these things in multiple domains. Geologists combined with computational people, and they develop these models. So, if there are no further questions, I would like to thank you all and the host and all the participants. I felt grateful for making this presentation. Thank you.
Thank you, sir. Thank you, Dr. Sarma, for sharing your views and your time with us. I would request Mihir, sir, if he is present, to speak a few words. I think, sir, one of the participant has a query. There is a raised hand by Aarti Singh.
Yes, please.
Aarti ma'am, can you raise a question?
Please.
I think she is unavailable at the time.
Okay.
Thank you once again, sir, for turning up. It was a pleasure to hear your presentation, and thank you very much, sir. You can leave now, sir.
Yes.
Thank you very much.